All right, and we're back. So this is a video going over the worksheet from yesterday, the back of the worksheet from yesterday. Make sure phones are up, people. Check, see? Make sure phones up. Brandon, no phone? No, no phone, Brandon?
I didn't get that paper.
It's right here. Here's Tommy trying to see his phone. Oh, I forgot. That's so like, oh, I forgot. Your phone, Henry?
I don't even know if it's
How do you not even know you have it?
No, I don't use
Because, I mean, he could have short-term memory loss. He could forget.
All right, let's start with number 8. Here we go. The perimeter of a triangle. Just like we had yesterday. You got a perimeter of a triangle equaling, looks like 60 inches. So the first side, let's label it. This is side 1, side 2, side 3. The first side is 4 inches shorter than the third side. All right, so what does the first side depend on? The third side. It's 4 inches shorter than the third. So if the third is x, let's put that there, then the first side is 4 inches shorter than that, x minus 4. And now our second side is twice the length of the first. So if it's twice the length of the first, well, that would be 2 times x minus 4, or in other words, 2x minus 8. So if the perimeter is 60, then we know that x minus 4 plus 2x minus 8 plus x is 60. Let's combine like terms. X, 2x, and x make 4x. Negative 4 and negative 8 make minus 12. And now we add the 12 over to the right side. So 4x is equal to 72. So if I divide by 4, that's 18. 18. Now, that's not, I think it's 18. Yep, 72 divided by 4 is 18. So now, let's check to see what they asked. Find the length of each side. Oh, okay. So I'm not looking for the longest or the shortest. I just want the whole length. So the first side is x minus 4. So 18 minus 4 is 14. The second side is 2x minus 8. Okay. But if it's double the first, then it's just 28. Expression for the third side is just x, so that means it's just 18. Those are my 3 answers. 14, 28, and 18. Questions? Are there any other questions that we'd like to go over? Yeah, Rick.
Number 5.
Number 5, the one on the top. Okay, let's take a look at number 5 up here. To start a collection of comic books, Joylyn's uncle gives her a box of comic books and several monthly subscriptions to comic books. The number of comic books in her collection, y, after x months, is modeled by the equation shown. Y is equal to 25 plus 4x. What does the number 25 represent in the equation?
I said how many comic books you already have from our uncle?
Good. Yeah. The original amount of comic books, the starting value of comic books, the comic books with before the subscription. That's good. What about the 4? What does the 4 represent? What does the 4 represent?
The amount she gets per month.
Good. And how many is that? 4. She gets. So we can say that represents the fact that she's getting 4 comic books per month. Good. The amount that she's getting per month. All right. Now, how many months will it take until she has 275? So 25 plus 4x is equal to 275. We subtract over the 25 to the right side, and that's 4x is equal to 250. And we divide by 4. So 250 divided by 4 is 62.5. All right.
Somehow I got 13. What is it? I got 13.
What's wrong?
I got 13.
How did you get 13? We did 25 plus, oh, it's not, oh yeah, it's 25 plus 4x is equal to 275, right?
Yeah.
You got what I got?
I got this.
Okay, good.
Yeah.
Maybe you just punched it in your calculator wrong. Maybe that's it.
Oh, I see. I put 50 and 250.
Oh, yeah, that would be an issue. Okay, so 62.5. Now, that means at 62 months, will she have 275 comic books?
No.
At 62 and a half months, will she have 275? No. No, there's no, they're not going to send you like half month subscription of comic books. No. It's going to be, it's coming at 1 month at a time. So, what's my true answer here? 63 months. 63 months. It's going to take her 5 years. All right. So, if you please put the keys back in the binders for the later periods. If you needed anything else to check for the second chapter, the binders are going to get cleaned out tonight, like the day after school. So please make sure that you do so sometime today.
Are we allowed to like cancel out some of our chapter 1 stuff?
Not yet. The only we can do a binder clean out at the semester time, because everything that we will cover this year will be like for the first semester. Everything will be on that first semester exam. So we should keep everything until we hit Christmas time. Okay. All right. So now let's continue on into chapter 3. So that being said, the binders are going to get cleaned out tomorrow to make room for the new chapter 3 keys to go in. So let's talk about chapter 3. Now, if I had to summarize chapter 3 in one statement, like what are we going to do in chapter 3? It's learning how to graph functions. And more importantly, learning how to graph linear functions. And all the different ways and all the different things that could happen. That's what we're going to be looking at in this chapter. How do we graph linear functions? That's what we'll be looking at. Well, the first thing that we should talk about then, if we're going to learn how to graph linear functions, is what the heck is a function? That's what we should look at first, okay? And if we got to understand what a function is, we should understand where it comes from, which is a relation. So let's first define ourselves a relation. Well, a relation is anything that pairs inputs with outputs. Anything. It could be mathematical. It may not be mathematical. It could be, the amount of hours I spend studying and my grade. Should there be a correlation? Probably. Does there have to be? No. But there should be some sort of a relationship. My age and how tall I am. Is that a relation? Yeah. Is it always increasing? No, because at some point you stop growing. The amount of miles I drive and the gas in my gas tank. That's an inverse relationship, right? One's going up as the other one's going down. But that's still a relationship. They give the example, the number of hours I work and the pay I receive from that work. That's definitely a relation. That's definitely a relation. The more amount of hours I work, the more my paycheck reads, right? The more amount of money is in my bank. Is there any other type of relation that you guys can think of? Can you think of any other relations? Give me a few examples. What other relations do we have? Could be anything. Could be relating two things to each other.
The amount of food you eat and the amount of energy you get.
Good. The amount of food you eat and the amount of energy you have. Right? More food you eat, more energy you have. Yeah. Depending on the type of food too. Though. You go to Taco Bell. I feel like when I eat bad, my energy goes down.
I'm just hungry.
Like the next day, I'm sluggish.
Yeah.
But if you eat healthier foods, I feel like I've got a little bit. What's another relation that we might have?
Eating healthy food and your energy.
Okay. Yeah.
Amount of sleep you get, and the amount of energy.
Yeah, okay. The amount of sleep you get and the energy that
I'm
you
just
have.
hungry and tired.
Hungry and tired. We all.
All
All right. Or I could think of it this way: the amount of hours you practice a sport and your ability. Right? That your ability is not really quantifiable. That's not really numerical, right? That's more of like a quality type thing. But the more you practice, the better you will be, right? So that is a relationship.
The more you study, the more you grasp the concept.
Good. The more you study, the more you grasp the concept. Again, not maybe numerical, not maybe grades, but yeah.
How much we throw away trash in the cycle compared to our
Here we go.
global warming rate.
Here we go again. Yes. All right. So let's take a look at this. The book gave us this example here. Let me make this a little bit bigger. And I don't know who puts cereal
In the vending
in it.
machine.
Just go with it here. Just go with it. Just go with it.
I think Mr. Spot put it in there.
All right.
Mr. Spot would put cereal in it.
So it says work with a partner, but you don't need to work with a partner. We're just going to talk through this as a class. This is an affirmation. What are two possible relationships demonstrated with this vending machine? Give me one. What is a relation that I could come up with for this vending machine?
The farther down you go in the vending machine, the higher up the price go.
Very good. The further down, now is there an exception to that rule? Maybe, yeah. But in general, yeah, the more higher priced items are generally on the bottom. Yep.
What number you put into what food you get out?
Good. What number you put into what food you get out, or what letter and number combination?
That's literally like you input something, you get it out.
Right. Yeah. Exactly. And that's what we're going to be talking about today too, right? But and that's the next question too. What are the inputs and what are the outputs? So the input would be, the letter and number I put in. The output would be what comes out of the vending machine.
How much money you put in the vending machine compared to how much money the vending machine eats.
Okay. Or takes in. Yeah. Okay. Good. Yeah.
If you got an orange juice, wouldn't it blow up when it fell?
Yes, yeah.
Carbonated. Well, no, not necessarily.
Wouldn't it candy and orange?
Well, I'm thinking like orange drink.
It would be like
Fanta.
dented.
Well,
Yeah, but
I guess so. But I mean, you guys ever get a pop can out of vending?
Yeah, but it usually
You
goes
never get a
up.
pop can? It doesn't like explode in there. It comes out. I mean, you got to be a little bit careful when you pop the top. Yeah.
The number of things purchased and the amount of pounds gained.
Okay. Yeah. Exactly. Because when you're at a vending machine, there's usually. But these look very healthy things. Look, there's an. That's like
Popcorn. Those are popcorn.
energy bar, protein bar, orange juice, grape juice, water. That's his energy
What's
drink.
the green thing?
Grace, they have Oscar coffees in there.
I thought those were cigarettes.
Now,
Yep, you get cigarettes out of a vending
Not
machine.
appropriate.
now, the funny thing you say that because there used to be like when I was young, I distinctly remember cigarette vending machines.
Seriously?
Yeah,
Well, I guess since kids can get
in
those.
certain places.
Yeah, since kids, those are easily accessed. I never think of like younger kids get
Exactly. All right, now we're talking about here relationships, right? I have a distinct thing that I am doing to initiate something happening, and then something will come back to me in the end, right? That is input versus output. That is putting something in versus getting something out. Now, let me ask you: is each of those relationships one input to one output? One input to one output. Like for example, I input the number and letter. Is it going to give me two different things?
No.
Unless I shake the machine real hard, right?
Yeah.
It's only going to spit out one thing to me. Now, let me ask you this. What if I input just the letter A? What are the possible outputs? Popcorn, nuts, or pretzel, right? Because aren't those all three A's?
Yeah.
So if I input A, there are 3 different possible outputs. That is not exactly one output. That, guys, please stop talking. That is not what I call a function. So let's define for ourselves what a function is. Now, in mathematics, a function is a relation that pairs each input value to one and only one output value. It pairs each input value to one and only one output value. Many times it's described as like a function box. I put in something, I get out something. I put in one thing, I get out one thing. You cannot put in one thing and get out 2 things. It doesn't make sense. That would not be a function. There are things that do that. There are things that have 2 different answers. For every 1 input, there is 2 outputs. Okay? Now, if I want to determine whether the relationships are functions, I have to examine and say, is it possible for me to get a second output for any input? So let's first, and we're going to examine it in a couple different ways. Let's first take a look at it through coordinates. And I'm going to ask you, is this a function? Look at the coordinates. If I have any x value, could I get 2 different values out with any one of my x values? Like if I said it this way. If my input was -2, what's my output? +2, right? If my input is -1, what's my output? +2. My input is -1, my output is +2. If my input is 0, what's my output? If my input is 1, what's my output? If my input is 2, what's my output? There's no second guessing any of those numbers, are there? That is a function. We can say, yes, that is a function. Each input has 1 output. And again, it's going to be important to explain your answer. A lot of the problems on your homework are simple yes or no questions, but it says to explain. I will not give you credit if you do not explain.
So, like, it doesn't have to be necessarily a pattern, it's just if you put something in and get something out?
Exactly. We'll talk about patterns soon,
Okay.
but not just quite yet. We're just talking about bare minimum here.
So, if we were to graph these and some of the outputs are the same, would that affect if it's an input or output?
So you're talking about, you're talking about like what happens like because these are the same?
Yeah.
That means they're going to kind of stack up horizontally, but not stack up vertically. And we'll talk about that in a
So
second.
they're not allowed to stack vertically, but they're allowed to stack horizontally?
Correct. You can have multiple of the same outputs. You just can't have multiple of the same inputs. Like, for example, take a look at this one here. Take a look at example B. Is this a function?
No.
No.
Why not? I hear a lot more no's than yeses. Why not? What makes it not a function?
Or the times that it's different outputs.
Very good. This is what makes it not a function. All of the other coordinates are completely fine. But the fact that 4 is in there twice and it gives me 2 different outputs for that 4, this makes it not a function. Okay, we would say not a function. Why? Because 4 has 2 outputs. Basically this, if I said what's the output when I plug in 4? Is there only one answer?
No.
No, that makes it not a function. Okay, let's take a look at the table. Is that a function?
No.
No, why not?
Because the 0 has 2 outputs?
Good. No, 0 has 2 outputs. Look, if I said if my input is 0, what's my output? You would say, well, it depends. Depends on which one you're asking about, 5 or 6. Now, this last thing down here is what's called a mapping diagram. A mapping diagram is used to tell if things are functions or not. Sometimes, basically it's just two ovals and all of the inputs go in one and all of the outputs go in another. So maybe I had like 2, 3, 4, 5 here, and then 6, 7, and 8 here. And I had arrows going from one to the next. Maybe we go there. If you only ever have one arrow coming out of an input, then it's a function. Like for example, looking at my original problem, what's the output if I plug in -1?
4.
4, no other option. What about 3? 15, no other option. What about 11? 15, no other option. It's okay that I'm going to the same output. That doesn't matter. And same thing here. Even in the one that I drew over here on the board, still a function. You know what would make it not a function anymore? Is if I did this. If I added in another arrow from 2, not a function anymore. Because then I would say, okay, what's my output if my input is 2? Well, there's 2 possible answers to that question. So we've talked about our definition of a function. We talked about it in logical terms. We talked about it with coordinates. We talked about it on tables. We talked about mapping diagrams. And now we're going to talk about it in terms of a graph. What does this look like visually? What does this look like in terms of a graph? Well, what we can use is this thing called the vertical line test. Now, the vertical line test tells us that if we can draw a vertical line anywhere on the graph and it hits twice, it's not a function. If we can draw a vertical line anywhere on the graph and it hits twice, it's not a function. So do you see how even though there's just these single solitary points, I could draw vertical lines through each one of those points and it's never going to hit another point. That's a function. Here, though, I draw a vertical line right there and I hit it twice. That's not a function. And that just has to happen once. Okay? There could be parts on the graph that it would look like a function, but then it might cut out on itself. Oh, not a function anymore.
So it's only vertical,
Vertical line test.
but it can't be horizontal.
Right. Horizontal line test tells you something else. And you'll learn that in Algebra 2. Okay, let's take a look here at example A. Is this a function? No, because I can draw this vertical line right there and it hits twice. So we say no. And the reason being it does not pass the VLT. You can abbreviate that, vertical line test. Again, you're testing whether it's a function or not by writing vertical lines on it. Yeah, we are on the top of the back page. For those of you zoned out. Now, is part B a function? Can I draw vertical lines everywhere? And it still only ever hit once? Yeah. Like I'm going to draw, okay, I wanted a dotted line, all right. I'm going to draw a dotted line and I'm going to move it. Is that ever going to hit more than once?
No.
No. It's only ever going to hit once. That's it. So we would say that yes, that is a function. And why? Because it passes the VLT, the vertical line test. Okay, visually, really quick. Is that a function?
No.
No, because I can draw a vertical line right here, hits twice, does not pass, so we would say no, doesn't pass, or fails the VLT. Again, you cannot just say yes or no on these questions. You have to give me a yes or no and then an explanation on why. To re-emphasize my point here about the fact that it could look like a function at certain spots, let me take a look at this graph. So if this was coming around and it went like this, and then I had that. Maybe you got this weird graph that looks like that. And I said, okay, is this a function? What would you say?
No.
No, but wait a second. It only hit once.
No.
Remember, it's got to be everywhere, right? So I should be able to move this vertical line and hits 3 times there, right? And then, oh, it goes back to only hitting once. Then it looks good and looks good and looks good. And then it looks like, ooh, kind of goes, looks like I hit twice there too. But then it's good the rest of the way. So even though it only happened in a short amount of time, that doesn't matter. It's still not a function anymore. Okay. All right, the last thing we'll talk about is domain and range. Domain and range. Now, domain of a function is the set of all possible input values, and the range of a function is the set of all possible output values. And I kind of let the cat out of the bag. Input means x values. Go ahead and write this in. Output means y values. Input is x values, output is y values. So when I ask you what is the domain, I'm asking you what are the possible things that I could plug into this equation, or what are the possible x values that I could have. If I'm talking about the range, I'm saying, okay, what are the possible y values that I could have? Now, we can usually like define them and talk about what they are. The issue is actually like writing it down on the page. Sometimes that gets a little tricky. Like for example, take a look at this first problem. Example A here. Take a look at these coordinates. I've got -3, -2. I've got -2, 0. I've got 1, 2, and then 3, 4. I hope we do know how to do coordinates, because that's not something that we talk about here. That's expected that you know it. All right, so you've got -3, -2, -2, 0, 1, 2, 3, 4. Now, the domain is the set of all x values, the set of all input values. So what is my domain here? -3, -2, 1, and 3. Do I want the points in between? No. All I want is just -3, -2, 1, and 3. That's it. I don't want +2 because it's not a point. So here's how I write it. I put a brace, -3, -2, 1, and 3. And just list out all of my x values. Yeah, Solomon.
Isn't -2 supposed to be -1?
Oh, whoops. I can't count. Thanks, Solomon. Sorry, math numbers aren't my thing, you know.
Yeah.
Right. Oh, said the math teacher. Thank you. All right, now let's talk about the range. Now the range are my y values. So what's my smallest y value? Well, I got to go to my lowest point vertically. -2. 0, 2, and then 4. So the domain of this equation, the domain of this function, and yes, I can call it a function, it passed the vertical line test, is -3, -1, 1, and 3. My range is -2, 0, 2, 4. Now, okay, I'm on example B, going to the right on your papers. What happens if it's a continuous graph? Because now, do I want all the points in between? Yes. Like, for example, -1 is part of my domain. It's on that line. What about 0? Yeah, it's still there. What about 1? Yep. 2, yep. 3, yep, but that's where it stops. 4?
No,
No. Okay, what about like 1.5?
I guess.
Yeah, what about 1.1?
Sure,
1.11?
sure.
Well, and so I could do that forever, right? So is it possible to list out all of my x values?
Yeah. No.
No. I couldn't, because I could keep doing that process of 1.1, 1.11, 1.111, and I could do that infinitely. So here's how we have to write it. If I want my domain, I go, okay, how far left can I go on this thing? What's my furthest left point? -2. What's my furthest right point? +3. Now, how do I write all points in between. Oh, that's a compound inequality. That's an and inequality. I want all points in the middle of -2 and +3. So whenever you have a continuous graph, you have to do this compound inequality. Now, looking at my range, that's top to bottom. That's verticality. That's here to here. So looking at my range now, what's the lowest point that I have?
-1.
-1. Highest point is 2. Now, instead of using x, what am I going to use? Yeah, just going to change that into a y. Now, that's only for when it's a continuous graph. That's only for when it's like a filled-in line. If it's single solitary points, you just list them out. If it's a continuous graph like that, you have to do an inequality.
Continuous graphs have the line connected.
Right, connected line. That's what I mean by that. Yeah. So is C continuous? No, it's just single points. So in that case, to write up my domain, I'm just going to use all of the x values. Okay, so -2 is an x value. Looks like -1 is an x value. 0 is an x value. 1 is an x value, and then 2 is an x value. Again, I don't care about how high or low it's going at that point, because all I care about is my domain, my initial x values. Let's talk about my range. Let's talk about my y values. Now, when I look at my y values, I'm going top to bottom, right? So what's my smallest y value that I have here? 0. Okay, my next y value up would be 2. Even though it's there twice, you don't write it twice, because you're just looking at like the set of the values. Then I have 4. Again, it's there twice, but you don't write it twice. Those are just the possible output values. Okay, for my last one here, is this a continuous graph? Is it a filled-in line?
Yeah.
Yeah. So therefore, I'm going to write it as an inequality. Okay, remember, domain is left to right. Now remember, when it's continuous, it should look like this. And I should put the smaller number on the left side and the bigger number on the right side. Okay, what's my smallest x value that I have? Write it like this. The smallest x value that I have is 1. The biggest x value that I have? 5. Then I do the same thing for my range. But instead of left to right, I'm looking top to bottom. Or really bottom to top, because I'm going smaller to bigger. What's the smallest y value that I have? 0. Goes all the way down here. And the biggest one I have is 4. So that's how domain and range works. You can take biggest or smallest to biggest, and you're just going to take, okay, furthest to the left, furthest to the right, furthest down, furthest up. That's my domain and range. All right. So we've talked about a lot about functions today. Tomorrow we're going to continue on in this section. The homework is over there, page 116, numbers 1 to 14. I'm giving you about 7 minutes to work. I'll pull up the book page here in a second after I turn off the video.
Goodbye.